In this video, I'm going to check if the function f of z, which is defined as z plus 1 over z, is analytic. To check if that given function is analytic, we have to check if it satisfies the Cauchy-Riemann equations. And the Cauchy-Riemann equations are the partial derivative of u with respect to x is equals to the partial derivative of v with respect to y. The second one is the partial derivative of u with respect to y is equals to minus the partial derivative of v with respect to x. Here, the u is the real part of the complex function and v is the imaginary part of the complex function. So the first step, we have to write our given f of z in the form f of z is equal to u of xy plus I multiplied by v of xy, where the u of xy is the real part and the v of xy is the imaginary part. A complex number is a number which can be written in the form z is equals to x plus iy, where x and y are real numbers and I is equals to the square root of minus 1. So we substitute this z into our function that we are having here. So we have x plus iy plus 1 divided by x plus iy. But to write now this function in the form where we have real parts and imaginary parts separated, what you can do is we multiply the numerator and denominator of this term by the complex conjugate of the denominator. So the complex conjugate of the denominator is x minus iy. And when we multiply that, we will get x plus iy plus x minus iy divided by x plus iy multiplied by x minus iy. Our expression simplifies to x plus iy plus x minus iy divided by x squared plus y squared. Now we go on and separate the real parts and imaginary parts, and we have the real parts will be x plus x divided by x squared plus y squared plus I multiplied by y minus y divided by x squared plus y squared. So we have now written the function in terms of the real parts on their own, the imaginary parts on their own. So looking at the expression that we have now, the real parts, we see that is these parts here. So that would be our u. So we have our u is equals to x plus x divided by x squared plus y squared. Our imaginary part, which will be the v is equals to y minus y divided by x squared plus y squared. So we now have our u and v. Then we go on and check if they satisfy the Cauchy-Riemann equations. So we have to take the partial derivative of this u with respect to x. But what you see is we have a quotient here. And when we have a quotient, you should know that we use the quotient rule to differentiate. So the derivative of this x here is just a 1. Then the derivative of this quotient, we use the quotient rule, which is here. And the result that we get is the partial derivative of u with respect to x is equals to 1 plus x squared plus y squared multiplied by 1 minus x times 2x divided by x squared plus y squared squared. Then when we simplify, we get 1 plus y squared minus x squared divided by x squared plus y squared squared. So that's our partial derivative of u with respect to x. We now go on and evaluate the partial derivative of u with respect to y, just because it's needed here for this equation. So for the partial derivative of u with respect to y, we differentiate this x with respect to y to give us a 0, then differentiate this quotient using the quotient rule, and we get the partial derivative of u with respect to y is equals to x squared plus y squared multiplied by 0 minus x times 2y divided by x squared plus y squared squared. And then when we simplify this part here, when we are multiplying by 0, it just gives us a 0. So we have the partial derivative of u with respect to y is equals to minus 2xy divided by x squared plus y squared squared. So we have our partial derivative of u with respect to y there. We now go on and look at the partial derivatives of v with respect to y, then with respect to x. So we have our v here. Take the partial derivative with respect to y. When you differentiate this y, we get a 1. Then to differentiate this quotient, we use the quotient rule here, and we get the partial derivative of v with respect to y is equal to 1 plus x squared plus y squared multiplied by minus 1 minus y multiplied by 2y divided by x squared plus y squared squared. And that will simplify to 1 plus y squared minus x squared divided by x squared plus y squared squared. So that's the partial derivative of v with respect to y. We now go on and evaluate the partial derivative of v with respect to x. So that will put it in this equation here. So we are differentiating this y with respect to x to give us a 0. Then for this part, this quotient here, we use our quotient rule, and we have the partial derivative of v with respect to x is equals to x squared plus y squared multiplied by 0 minus y multiplied by 2x divided by x squared plus y squared squared. And then when you simplify, we get the partial derivative of v with respect to x is equals to 2xy divided by x squared plus y squared squared. So we now have those 4 partial derivatives. Now let us go on and look at this one here, the partial derivative of u with respect to x. We see that it is equal to this partial derivative of v with respect to y. So it is satisfying this equation here, the first one. Then we go on and look at this equation here, the partial derivative of u with respect to y. Compare it with the partial derivative of v with respect to x. We see that the partial derivative of u with respect to y is equals to minus the partial derivative of v with respect to x. So what we are having there is the Cauchy-Riemann equations are being satisfied. So the function f of z is analytic. But what we have to note there is the f of z is analytic if we're in the complex plane except at x equals to 0 and y equals to 0. The reason being, if we look at the denominator of these partial derivatives, they are not defined when x and y are equal to 0. So what we have there is f of z is analytic everywhere in the complex plane except at x equals to 0 and y equals to 0.